An RC circuit is a circuit that contains resistance and capacitance. So we'll be looking at the behavioral tendencies of this network. Alright, so first of all, let's look at charging the RC circuit. So if we have a circuit like this is our voltage source, we have our resistor, and we have a capacitor connected like this. Okay, so this is our RC network. Then we have a switch. Alright, so this switch can toggle between the voltage source or the negative. So when we have the switch on the side of the voltage source, the switch charges up this network. And when we have the switch on the side of the negative, the switch then helps discharge this network. So let's go into the equations involved with this charging. And these equations were derived by Kirchhoff's law. Okay, so the first one, for charging the capacitor, we have Q equal to CV 1 minus e raised to the power minus 1 over RC, which is also equal to Q 1 minus e raised to the power 1 divided by tau. Tau is equal to RC, where R is the value of our resistor and C is the value of our capacitor. So multiplying both values will give us tau, which is called the time constant. We can get the voltage difference across this capacitor by applying this formula: V times I minus E raised to the power minus T over tau. Okay, if we solve for that, we'll get the voltage across this capacitor. If we use this formula, we get the voltage across this resistor, which is IR times E raised to the power minus T over tau, which is same thing as V times E raised to the power minus T over tau. Alright, so we have this as our voltage. So I0 here is our current, the current supplied by our voltage source. R is this resistance, the value of this resistor. Alright, then we have, of course, tau to be value of this resistor times value of the capacitor. So we can simplify this to be V E raised to the power minus T over tau. So the current through the resistor, which is same as the current through the capacitor, because they are both in series. So any amount of current that goes through the resistor will be same amount of current that gets to the plate of the capacitor. And we have the formula to be I0 e raised to the power minus T over tau. So still talking about charging the network, let's look at the graphical representation of elements in this network with respect to time. Okay, how they respond with respect to time. So the first one, the diagram for charge versus time. But here we don't just have time, we have the time constants. So at this point we have 0, then we have 1 time constant, and here 2 time constants, here 3 time constants, here 4 time constants, here 5 time constants. Okay, this is not just time, this is time constants. Alright, it's different from time. Tau is different from T. Charging this capacitor from 0 to when it's full will take approximately 5 time constants. So you can see this is charge per time. Once this capacitor starts charging, the voltage increases like this. You see, it's not a one-time thing. The capacitor doesn't just charge up like instantaneously. Okay, it goes through this exponential curve. So charging the capacitor is exponential. So at 5 time constants, it's approximately full. So this point is the amount of charge that has gone in at 1 time constant. This is the amount of charge that has gone in at 2 time constants, this for 3, 4, and this for 5. Alright, so we see this is the transient state. This is where it's transiting into stability, while at this point it gets to a steady state and it just goes flat from there. Alright, so this is the formula that we're given on the other slide for getting the charge. So we can use this formula to get the particular charge that would have gotten into the capacitor at a particular time, at a given time. So the next one we'll be looking at is, we have for capacitor voltage versus time. Alright, it has the same curve as the charge versus time. Okay, and this is the formula. We can use this formula, of course they're all exponential curves. We can use this formula for finding whatever we need to find, okay, regarding time and voltage. Okay, what time it will be at a particular voltage, or what voltage at a particular time. We can use this equation to find that. Then we have for the capacitor current versus time, we have this. Okay, so we see that the current flowing into the capacitor at the beginning is its maximum, which is 100%. You have maximum current flowing into the capacitor from the time you toggle the switch to the voltage source. Okay, but then that current continues to drop until the capacitor can take no more. So we can see that at 5 time constants, the capacitor is full, all right, approximately full. So we can use this formula that was given to also find whatever I want to find regarding how much current the capacitor takes at what particular time and all that. We can see that at 1 time constant, we have our current drop to 36.8%. Okay, at 2 time constants, we have it drop to about 13.5% and it continues with that trend until it gets to 0.6, while we have the resistor voltage versus time. So we see that the voltage of the resistor, the voltage across the resistor, is at its max at the beginning, because of course the capacitor acts as a short once the voltage difference is found across its ends, and that's because it needs to charge, so it pulls in the maximum current which it can pull at the beginning and starts dropping from there. So we're going to have this wire here to be at zero potential at the beginning, just when this thing starts taking in current, because it's going to act like it's short. So if we consider the voltage on this side with respect to the voltage on this side, we'll have this resistor at maximum voltage just when you switch this on. And as this guy continues to charge, this place will begin to build up voltage and then reduce the voltage reading across both ends. So we look at discharging the RLC network. So we have our switch toggled to the negative, alright? So the equations we get would be, for getting the charge from the capacitor, okay, the charge gotten from the capacitor while discharging will be Q times e raised power minus t over tau. The voltage difference across the capacitor, alright, will be V0 times e raised power minus t over tau, alright. So we can use that formula to get the voltage difference at any given time. Then we have that across the resistor to be V0 times e raised power minus t over tau, and we have the current through the resistor to be minus I0 e raised power minus t over tau. But then we have the graphs for discharging. We have the capacitor current versus time. We see that in this case we have our graph like this. Compared to the charging, it was this way. Okay, so we have it like this, and this is the formula we got from the previous slide for the capacitor current. This is also the same formula, the same graph for the resistor current, because the current flowing to the resistor is same as that flowing through the capacitor because they are in series. Okay, then we have the resistor voltage versus time to be this graph, and we have capacitor charge versus time, we have resistor voltage versus time, okay, with their different formulas. What are the uses of the RLC circuits? Okay, first of all, they can be used for timers. Alright, so because of how the behavior of this network is, we can use them to time certain things in our circuits. Okay, so what we can do is, we know how long it will take the capacitor to charge up to a certain voltage, so we can use that by tracking the voltage of the capacitor pin. Knowing the voltage on the pin, we can just know how much time has gone by. Alright, so we can then trigger an effect based on whatever it is we want. So we have pacemakers. Alright, we can use them to make pacemakers. Okay, and we also have filters. Okay, they can be used to filter circuits from noise. Especially you would see them a lot in the input of SMPS circuits. We have filters there, and you will find capacitors and resistors as filters used to help reduce noise from the circuit. So we'll be looking at this question in our next video, and we're going to build the circuit and see for ourselves that this thing actually is what it is. See you in the next video.